What if you could take an ordinary video, upload it to a website, and automatically get back a professionally subtitled version of that video? That's exactly what we're gonna build in this project. We're not just gonna write a few lines of code and call an API. We're gonna build the entire pipeline from scratch. We'll use FastAPI to create the web application, Whisper to transcribe it, Gemma to intelligently improve the subtitles, SRT to organize the captions, and FFmpeg to permanently burn those subtitles into the video. And then on top of all of that, we will build a clean web interface where the user can simply choose a video, upload it, wait for processing, and download the final result. By the end of this project, you won't just understand individual technologies. You will understand how all of these components work together to create a real AI-powered application from beginning to end. So let's build it. Here we created a new folder for our project and named it Video Subtitles Generator, then open it with VS Code. Before building our AI subtitle generator, we first need to prepare the development environment. Since this project combines speech recognition, large language models, video processing, and web interface, we need a clean and isolated Python environment to manage all dependencies. First, we create a virtual environment using Python's built-in VNV module. A virtual environment keeps our project library separated from the rest of our system, which makes the project easier to maintain and deploy later. After creating the environment, we activate it. You can see that the terminal now shows the environment name, which means all packages we install from this point will belong to this project. Now let's install the core dependencies. The first one is FFmpeg. FFmpeg is responsible for the video processing part of our pipeline. It allows us to extract audio from videos, combine subtitles with the video, and generate the final output file. And here it is. We create a folder in which we're gonna put all our Python files for our pipeline. We call it modules. Okay, and in this folder we're gonna create audio. Okay. Alright, now we are entering one of the most important stages of our subtitle generation pipeline, which is audio extraction. Before our AI can generate subtitles, it first needs something it can actually understand, and that is audio. A video file contains many different components: visual frames, audio streams, metadata, and sometimes even subtitles already embedded inside the file. But speech recognition models only care about the audio portion. So in this module, we are going to extract the audio from the uploaded video using FFmpeg. Let's start by importing the first needed library, which is FFmpeg. So import FFmpeg. Now, FFmpeg is an extremely powerful multimedia processing tool used all over the world for video editing, streaming, compression, audio extraction, subtitle rendering, and much more. In fact, many professional media systems internally rely on FFmpeg. So by learning FFmpeg, you are actually learning a real industry level tool. This function is called extract audio. The goal of this function is simple. Take a video file and generate an audio file from it. Now, notice that the function receives two parameters. Video path, this is the location of the input video. For example, movie.mp4, and audio path, and this is where we want to save the extracted audio, for example audio.mp3. Now we have reached the core processing line of this module. Although this looks like a single line, several important things are happening here. First, FFmpeg input video path. This loads the video into the FFmpeg processing pipeline. At this stage, FFmpeg can access the video stream, the audio stream, and the file metadata. Next, output audio path. This tells FFmpeg where we want to save the extracted audio. For example, if the input is an MP4 video, the output might become an MP3 audio file. Finally, run override output. .run actually executes the FFmpeg command. Without .run, nothing would happen. The pipeline would only be defined, not executed. And then we have override output equals true. Normally, if a file already exists, FFmpeg asks for confirmation before replacing it, but in backend systems and automation pipelines, we don't want the server waiting for manual user input, so we set override output equals true. This automatically replaces old files if they already exist. Next, return. This is very important for pipeline engineering because the next module in our application needs to know where the generated audio file is located. Finally, we test our code by giving it a video and see if everything works well. Okay, now let's test our code. So I'm gonna call the function extract audio, and now let's run our code. Oops, let me add the video first. I'm gonna put it in the directory. Okay, here's one of my videos. It's a very short video. So I'm gonna put the video inside modules, okay, modules, and then I'm gonna add modules here. Okay, and now we are gonna test our code. Okay, and as you see here, we got the audio file. Perfect. We have successfully extracted the audio from our video. Now comes the heart of our subtitle generation system, which is speech recognition. In this module, we are going to transform raw audio into readable text using AI. And for that, we will use one of the most powerful open source speech recognition models available today. We're gonna use OpenAI Whisper. So let's install it first. After installing it, we are gonna create a file and name it transcriber.py, and then we import Whisper. This imports the Whisper library. Whisper is an AI speech recognition system designed for speech-to-text conversion, multilingual transcription, language detection, and timestamp generation. In simple terms, it listens to audios and converts spoken language into text. Next, we load our AI model. This line is extremely important. Here we are loading the Whisper model into memory. Think of a model like a trained AI brain. Before we can perform transcription, we must first load the trained neural network. And turbo means we are using the turbo version of Whisper. Different models have different trade-offs. So in our application, we are choosing a model that gives us a good balance between speed and transcription quality. Next, we define our transcription function. This function takes one parameter, audio path, which is simply the location of the audio file we generated in the previous module called extracted audio.mp3. Now we reach the core line of this entire module, which is result. This is where the AI actually performs speech recognition. When this line runs, Whisper performs several operations internally. Whisper listens to the audio, analyzes speech patterns, recognizes spoken words, and generates transcription result. After transcription, Whisper returns a structured result object. This object contains lots of information, for example, detected language, full transcription, confidence data, speech segment, and time stamps. But for our subtitle application, we are mainly interested in one thing, which is segment. This list will store our cleaned subtitle data. Inside the list, we build a dictionary for each speech segment. This contains the actual spoken words. For example, hello everyone, welcome to the tutorial. This line indicates when the speech begins. For example, 10.15 seconds. And this line indicates when the speech ends. For example, 15.82 seconds. Well, why timestamps matter? Well, this is extremely important for subtitle systems. Subtitles are not just text, they must be synchronized with the video. If timing is wrong, subtitles appear too early or too late. So timestamps are essential. Now, notice the syntax. This is called a list comprehension in Python. Instead of writing a long traditional loop, we create the list in a concise and readable way. It does exactly the same thing if we do it in the traditional way. We use list comprehension to make the code shorter, cleaner, and easier to read. Finally, we return our processed subtitle segment. This is critical for our application pipeline. The next module will consume this segment. Notice something important about this module. Its responsibility is very focused. It does one thing, which is speech transcription. It does not extract audio, format subtitles, render videos, and so on and so forth. This is clear modular design. This file is actually where the intelligence of our application begins. Until now, we were mainly processing media files, but here we are using a trained neural network to understand human speech. This is the AI layer of the system. So, great, we now have timestamped speech segments extracted from our audio. The next challenge is making those transcripts cleaner, more readable, and better suited for subtitle presentation. And that's exactly what we will build in the next module. We now have timestamp transcript coming from our speech recognition system. But raw transcription is not always perfect. Sometimes subtitles contain missing punctuation, awkward sentence structure, formatting issues, or readability problems. So in this module, we are going to integrate an LLM, a large language model, to intelligently improve our subtitles. And for this project, we will use Gemma running locally through Ollama. If it is not convenient for you to use local LLMs, you can access other LLMs via an API. Before we write the code, let's understand where this module sits inside our application pipeline. Whisper gives us raw transcription. Gemma acts like an intelligent editor that cleans and improves the text. Let's create a new Python file and name it Gemma API and begin with the import. So we import request, and we also import JSON. So for request, this is one of the most popular Python libraries for making HTTP requests. Think of it as Python's way of talking to web services. We use it for APIs, backend communication, model servers, and cloud services. In this case, we are using it to communicate with our locally running AI model. If you don't have it installed, you have to install it first through pip install request. In this case, we are using Gemma through Ollama. So if you don't have Ollama, install it first, then download Gemma as our local LLM. So for those who use Mac OS or Windows, you can download it through this link, or you can also download it manually from this link. Then you type Ollama pool and you choose the large language model version you want to use. In my case, I already have Ollama installed and Gemma downloaded, so let's check first. As you can see here, these are the LLMs I have on my computer. For JSON, it stands for JavaScript Object Notation. It's one of the most common formats used for exchanging structured data between systems. APIs commonly send and receive JSON. Next, we define our function. This function takes one parameter, which is prompt. The prompt is the instruction we send to our large language model. For example, fix punctuation and improve subtitle readability, or convert this transcript into clean subtitles. These are possible prompts we can send to our LLM. Now we define the API endpoint. URL. This line is extremely important. Here we are connecting to localhost. Localhost means the AI server is running on our own machine, not cloud API, remote server, or internet service. Everything happens locally. This number is called a port. Okay, think of ports as doors into software services. Ollama opens this port so external applications can send requests to the language model, and API generate. This endpoint tells Ollama generate a response from the model. Next, we build the request payload. Payload is actually the data we send to the AI model. First, model Gemma 4. This tells Ollama which model to use. Different possibilities could be Gemma 2, Gemma 4, and so on and so forth. Think of this like choosing which AI brain you want to activate. Next, prompt. Prompt sends our instruction to the large language model. The prompt is the heart of LLM applications. It defines task, behavior, and expected output. Then stream. Some LLM systems support streaming output. That means token arrive progressively, so we disable streaming. Next, format. This is very important. We are forcing the language model to return valid JSON because applications prefer structured data. Instead of receiving massive free text, we receive machine-readable output. Now we actually contact the model. This is where backend to AI communication happens. Here we are sending an HTTP post request. Post means we send data to a server. In our case, we have application, Olama, and Gemma model. Next, we validate the response. This checks whether the request succeeded. HTTP responses use status codes, for example, 500 for server error, 200 for success, 404 for not found, and so on and so forth. So here, 200 means everything worked correctly. Now let's unpack the result. Response.json. This converts the API response into a Python dictionary. And next we have response. This accesses the actual text generated by Gemma. Then we do something interesting here because Gemma returns a JSON string, but Python still sees it as text. So we convert that text into a real Python dictionary. For example, before it might look something like this, but after it looks like this. Finally, we handle failure cases. If the model crashes, the API fails, or Olama is not running, we return an error message. This is basic defensive programming. Notice something important. This module has one responsibility, which is communicating with the language model. It does not transcribe audio, generate subtitles, and render videos. This separation makes the system cleaner and easier to maintain. This module demonstrates a very common architecture used in modern AI systems, as you can see here, which is a pattern used everywhere like AI assistants, chatbots, enterprise AI systems, and document processing platforms. In production systems, we could improve this module further, we can add timeout handling, retries, async request, authentication, login, exception handling, and there are so many others we can add. Great, we now have an AI-powered subtitle enhancement system. The next step is transforming this clean transcript into a proper subtitle format with timestamps. And that's exactly what we will build in the next module. On our way to building our subtitle enhancement module, a very important question arises. How do we guarantee that every subtitle follows the same structure? Because in backend systems, consistency matters. We don't want random dictionaries floating around with missing fields or unexpected format. To solve this problem, we use schemas. Let's create a new Python file and name it schemas. And start by importing Pydantic from. If you don't have it installed, you have to install it first. So let's install it. Pip install Pydantic. So here we import base model from the Pydantic library. So what is Pydantic? Pydantic is one of the most popular Python libraries for data validation, schema definition, structured backend models, and API data handling. It is used extensively in modern backend development, especially in FastAPI, AI systems, backend APIs, and production Python applications. Let's make it simple. Think of Pydantic as a data quality inspector. Before data enters your system, Pydantic checks if the object match the required structure. Now we define our schema. This creates a new class called Caption, and it inherits from base model. This is actually called inheritance in object-oriented programming, which means our class receives functionality from Pydantic's base model. By inheriting from base model, we automatically gain validation, type checking, serialization, structured data handling without writing extra code. Now we define the fields inside our subtitle object. Okay, let's explain it one by one. First, ID. This defines a subtitle identifier, for example, C0, C1, C2, and so on and so forth. Str means, or str means string data type or textual data. This field helps uniquely identify each subtitle. Next, text. This stores the subtitle content itself. This is the actual text viewers will see on screen. Next, start, and here we have float. This stores the subtitle start time. Float means floating point number. Numbers with decimals, for example 2.35. We use float because subtitle timing requires precision. Milliseconds matter. Next, end, and it's also float. This stores when the subtitle disappears. So start and end together create subtitle synchronization. Finally, we have a style, and here we set it to dictionary. Okay, dict, which stores subtitle styling information. Dict means dictionary data structure or key value storage. In our current project, style is gonna be empty. Possible future uses might be subtitle colors, font customization, animation, positioning, or effect. At this point, our application can already do speech recognition. We extract audio, we send it through Whisper, and we obtain timestamp transcription segment. But there's still a problem. Raw AI transcription is often not ideal for subtitles. Sometimes we get awkward phrasing, missing punctuation, inconsistent capitalization, or reduced readability. So in the next module, we are going to build a subtitle enhancement layer using a language model. Before we write the code, let's understand where this module lives inside our overall application pipeline. This module acts as an intelligent subtitle editor. So we're gonna create a Python file here inside modules, okay, and call it captioner. Okay, and we begin with the import. So let's import the function we created in here in Gemma API, which is called Gemma. Okay, so from Gemma. Okay, and we also import caption from schemas. So here we imported call Gemma. This function allows our application to talk to the Gemma language model. Remember, we actually built this module earlier. Its job is to send prompt to Llama and retrieve AI responses. Next, we import the caption schema. This one. This defines the structure of our subtitle object. And now we create the main function. Well, this function receives a segment. These are the transcription chunks generated by Whisper. Next, we initialize an empty list. This list will store our enhanced subtitle object. At the beginning, the list is empty. Later, we will fill it with improved captions. Now we iterate through every transcription segment. For I. So this uses Python's enumerate function because we want the subtitle data itself and its numerical position. I stores the subtitle index, like for example 0 for the first subtitle, 1 for the second subtitle, and 2 for the third subtitle, and so on and so forth. And seg stores the current transcription segment. Okay, now we reach one of the most important parts of this file, which is the prompt. Here we are dynamically constructing an LLM prompt. The F before the triple quote means formatted string. It allows us to inject variables directly inside text. So now let's write the prompt. Improve. So this defines the task. We are asking the LLM to improve readability, not rewrite everything. Now comes the safety layer. Let's call it critical rules. So this is actually prompt engineering. Without strong constraint, LLMs often become creative, and creativity is dangerous for subtitles. We do not want translation, summarization, hallucination, or altered meaning. We only want gentle refinement. Now we inject the current subtitle. Well, this inserts the transcription text inside the prompt. Now we send the prompt to the language model. Improved. This is where the AI enhancement actually happens. And now we validate the returned result. This checks if Gemma returns a dictionary object. Is instance actually checks object types. Next, we safely extract the generated text. Here we have improve.get. This retrieves the text field. Using .get is safer than direct indexing. For example, like this one. Okay, so using get is much safer. If we use the other way, our code will crash if text does not exist. But using .get, we will get an empty string as a fallback. Now we handle another possible failure case. .strip removes surrounding white space. For example, if you have something like this, it's gonna return something like this. The fallback logic here is that if the model produces nothing useful, we revert back to the original transcription. This is defensive programming. Never lose the subtitle. Now we build our subtitle object. Here we have created a structured subtitle object using schemas we created earlier. This creates unique caption IDs, for example, C0, C1, C2, C3, etc. And this stores the improved subtitle. And here we have the timestamps. We preserve synchronization timing. This is very important. And here we have the style field. This reserves space for future subtitle styling. Possible future uses can be colors, positioning, font, animations, so on and so forth. Finally, we return our enhanced caption collection. These captions will be passed into the next stage of the pipeline. We now have clean AI-enhanced subtitle object with timestamps. The next step is converting these captions into a proper subtitle file format like SRT, and that's exactly what we will build in the next module. We now have clean AI-enhanced captions with timestamps. But there's still one more important step left. Our subtitles currently exist as Python object inside our application, Video players cannot directly understand Python object. They need a standard subtitle format, and one of the most common subtitle formats in the world is SRT, subrip subtitle format. So in this module, we are going to convert our captions into a valid SRT file. For that, we are gonna create another Python file. Before writing the code, let's see where this module fits into our overall pipeline. This module is responsible for converting our internal caption data into an industry standard subtitle file. Let's begin with the main function, def. This function receives captions. These are the structured caption object generated in the previous module. Our goal is simple. Convert these caption object into properly formatted subtitle text. Now we add another function here. Okay, now we encounter something interesting. This is a nested function. This means we create a helper function inside another function. Why do we do this? Because time formatting is a small internal task. It only exists to help the SRT conversion process. We don't need this helper function outside this module. Before we write the math, let's explain the required subtitle format. SRT files require timestamps in a very strict structure, like the one you see on the screen. You can see hours, minutes, seconds, and milliseconds. Let's give an example here. For example, here we have 1 hour, 25 minutes, 10 seconds, and 200 milliseconds. This formatting must be precise, otherwise video players may reject the subtitle file. Okay, now let's format our timestamps. First, we start with hour, integer, t. So here, 3600 seconds equals 1 hour. We use floor division. We use slash, which is floor division. It gives us the whole number of hours. Okay, next one. So m, which is minute, integer, t. This calculates minute. T modulo 3600 removes complete hours. For example, 7265 modulo 3600 equals 65. And now we divide by 60 because 60 seconds equals 1 minute. Next we calculate seconds. Integer t. This extract remaining seconds. Now the most precise component is milliseconds. So let's calculate it. So this calculates milliseconds. Integer here removes decimals, and t minus integer t isolate fractional seconds. And then times 1000 convert to milliseconds. Now we generate the final SRT timestamp. Okay, this uses an F string with formatting specifiers. 02 means minimum width, which is 2 digits. Without formatting, we may have like 5, but with formatting, we have 05. The same here, 03 ensures 3 digits. And the final output may look something like this. And this is exactly what SRT requires. Now we create an empty string. This will hold the complete subtitle file content. Initially, it's empty. We will gradually build it subtitle by subtitle. Next, we process every caption. For I, C in enumerate captions. Again, we use enumerate here because we need the subtitle number and caption data. For example, 0 is the first caption and 1 is the second caption. And then we generate the subtitle index. SRT. SRT files require numbering, like 1, 2, 3, 4. The reason why we added 1 is that Python starts counting from 0, but subtitle numbering starts from 1. Okay, then SRT. Alright, and here we have the timing information. This generates something like this. So remember that we called format underscore time twice, once for start time and once for end time. This creates subtitle synchronization. Without this line, the subtitles would have no timing. Now we add the actual caption. C.text is the actual caption, okay, which is the actual text, and NN here is 2 lines, okay. The double new line is intentional. SRT files separate subtitle blocks using lines. So the correct structure looks something like this. Finally, we return the completed subtitle file. At this point, our subtitles are now in standard SRT format, ready for media players, video editors, subtitle rendering systems, and much more. We now have fully formatted subtitle files. The next step is taking these subtitles and embedding them into our final rendered video. At this point, our application has extracted audio, generated transcription, enhanced captions using AI, and created a valid SRT subtitle file. Now we reach the final stage of the entire pipeline, which is video rendering. This is where we permanently burn the subtitles into the video. First, let's understand where this module fits inside our complete application. This is the final production stage. Now we create another Python file and name it render.py. And let's begin with the import. First, we import subprocess. This is one of Python's most powerful system programming libraries. It allows Python to execute internal commands, launch external programs, and communicate with operating system processes. Remember, FFmpeg is fundamentally a command line application, so our Python application needs a way to launch it. That's exactly what a subprocess does. Now let's define our rendering function. This function receives 3 input: video path, which is the original input video, SRT path, which is the generated subtitle file, and output path, which is the final rendered video destination. Now we construct the FFmpeg command. Instead of writing one long terminal command, we build it as a Python list. This is safer and cleaner. The first item, FFmpeg, tells Python which external program to run. Why? This flag means overwrite existing output automatically. Backend systems should run automatically, no manual confirmation. Next, I video path. This specifies the input file. And here we reach the most important rendering line. VF. Okay, VF means video filter. Filters allow FFmpeg to modify video frames like scaling, cropping, overlays, and subtitle burning. The first filter is scale 1080 and -2. This resizes the video. It means the width is 1080 pixels and the high is automatically calculated. -2 ensures the high is divisible by 2, which is required by many codecs like H.264. You can choose the resolution you want. If you want a higher quality video, you can choose a higher resolution. Next, subtitles. This is where subtitle rendering happens. If FFmpeg reads the SRT file, then synchronizes timestamps, overlays text, and embeds subtitles into frames. Next, CV. This selects the video codec. A codec compresses and encodes video data like H264, H265, VP9, and AV1. These are all codecs. You have to choose the codec according to your hardware and operating system. Here we use H264 Video Toolbox. This is Apple hardware acceleration. It uses the Mac GPU and media engine for faster rendering, which is actually much faster than pure CPU encoding. Next, we have CA and copy. This handles audio. We are telling FFmpeg to copy audio directly, no re-rendering. This results in faster processing and preserves original audio quality. The final command item is output path. This defines where the rendered video will be saved. Now that we have created our FFmpeg command, we need Python to actually execute it. This is where subprocess.run comes in. The subprocess module allows Python to communicate with external programs installed on our computer. In our case, as we said earlier, the external program is FFmpeg. Instead of manually opening the terminal and writing FFmpeg I input.mp4, Python can run this command automatically. Let's look at each parameter. First, cmd. This is the command we actually created. When we pass this list to subprocess.run, Python executes the same command as we typed in the terminal. The next parameter is stdout equals subprocess.devnull. Stdout means standard output. Normally, when FFmpeg runs, it prints information to the terminal. This is useful when we are debugging, but in a production application, we usually do not want all these messages appearing on the screen. So subprocess.devnull means ignore the normal output and throw it away. In other words, FFmpeg can continue working, but Python does not display these messages. The next parameter is stdr equals subprocess.pipe. Now this one is different. FFmpeg sends many important messages through stdr, including errors. For example, error opening input file or invalid subtitle file. Instead of showing these messages directly, we capture them inside Python. Pipe create a connection between FFmpeg and our Python program. Later, if something goes wrong, we can read these messages. The last parameter is text, which is set to true. It actually controls the format of the captured output. Without this option, Python receives bytes. But with text true, Python receives a normal string, which is much easier to work with. After FFmpeg finishes, subprocess.run returns a result object. This object contains information about the execution, which tells us whether FFmpeg succeeded or failed. Now let's check. F result. So a return code of 0 means success. Anything else means there was an error. For example, 1 might mean the input video does not exist, or the subtitle file is invalid, or FFmpeg failed during encoding. If an error happens, we stop the program and display the error message. This is much better than silently producing a broken output file. Finally, return output path, which means the function returns the location of the generated video. Now, the next part of our application knows where to find the finished video. So, the complete workflow is Python creates the FFmpeg command, subprocess.run sends this command to FFmpeg, FFmpeg renders the video, Python captures possible errors, and if everything is successful, the output video path is returned. This small piece of code is the bridge between our Python AI pipeline and the powerful FFmpeg video processing engine. Up until now, we have been building individual modules. Each file had a specific responsibility, but now we need something that orchestrates everything together. For this purpose, we're gonna create a new Python file and name it pipeline.py, but this time we're gonna create it outside the modules folder, pipeline.py. And then we're gonna move this video out of the modules folder. Okay. This file is essentially the central brain of our application. Then inside the modules folder, we add __init__.py. This is very important in Python. It turns the folder into a Python package. Without it, Python would not properly recognize modules as an importable package in many project setups. Because of __init__.py, we can write imports like from modules.audio import extract audio instead of messy manual path handling. This is standard Python project organization. Now let's start the actual pipeline implementation. So as we said, this file is the orchestrator of our entire video subtitle generation application. We already have different modules responsible for different tasks. For example, the audio module extract the audio. The transcription module uses Whisper. The captioning module uses Gemma. And the SRT module creates the subtitle file. And the rendering module uses FFmpeg to generate the final video. Our pipeline.py will connect all of these components together. So let's start. First, we need OS because we will use it later to check whether the output video exists and to get its file size. Okay, import OS. Okay, and now we import the function responsible for extracting the audio. So from modules. Next, we import our transcription function from. Then we import the function that improves our captions using Gemma. Okay, from. Next, we import the function that converts our captions into SRT format from. And finally, we import the function that renders the subtitles onto the video from. Now let's create our main pipeline function. This function will receive the path of the video that we want to process. So def. The first thing we need to do is extract the audio from the video. Before calling our audio function, we need to create the path for the audio file. So we're going to replace the .mp4 extension with .mp3 audio. Now we can call our audio extraction function. We provide the original video path and the path where we want to save the extracted audio. So audio. Now the audio has been extracted, so we can move to the transcription step. We pass the extracted audio to Whisper through our transcription function. So data The result is stored in data. This contains the transcription segment returned by Whisper, including the text and the timing information for each segment. Now we want to improve those raw transcription segments. We pass them to our caption enhancement function. Captions. The result is stored in captions. These are our final caption object, which contains the improved text together with the original timing information. Now we need to convert this caption object into SRT format. So we call our SRT function. So SRT. This gives us the complete SRT content as a string. Next, we need to determine where we are going to save the SRT file. Again, we will replace .mp4 with .srt. SRT. Now we can open the SRT file in write mode. So with open, and inside this block, we'll write our generated SRT content into the file. At this point, our subtitle file has been created. Now we move to the final stage, which is rendering the subtitles onto the video. First, we will create the path for our output video. So we will replace the mp4 with _out.mp4. So let's do it. Out mp4. Okay, this is the final output video that we are gonna get. Now we will call our rendering function. We provide the original video, the SRT file, and the output path. Okay, render. The rendering module will use FFmpeg to process the video and burn the subtitles directly on it. Now that the rendering is finished, we should verify that the output video actually exists. We will use os.path.exist for this. If not, if the file doesn't exist, we will raise an exception. Raise. Alright. Next, let's check the size of the output file. We can use os.path.getSize. So size. And we will use a simply sanity check. If the output file is extremely small, we will assume that something went wrong during rendering. If size is less than 10,000 bytes, raise exception. Okay, so if that's the case, we will raise an exception here. If we have reached this point, our pipeline has successfully completed all 5 stages. Now we return the 3 important results, which are captions, SRT, path, and finally output path. I hope I didn't make any typo. So the function returns our captions, the SRT path, and the final video path. Now we need to decide when this pipeline should actually run. For that, we will use Python standard __name __ check. So if this means the following code will execute when we run pipeline.py directly. Now we will call our pipeline and provide the video we want to process. Sorry, there is a typo here. And then we actually pass the video, which is this video, 0408.mp4, 0408.mp4. Okay, finally let's print the results so we can see what the pipeline produced. First, we will print the captions. Print captions. All right, and then we give it captions. All right, these are the captions returned here, and then we will print the location of the SRT file. Print SRT saved at, and then we give it SRT path. And finally, we will print the location of the rendered video. So print video saved at, okay, and we give it output path. And that's our complete pipeline. The important idea to remember is that pipeline.py is not responsible for doing all the individual tasks itself. Instead, it acts as the orchestrator. It calls the audio module, then the transcription module, then the caption enhancement module, then the SRT module, and finally the rendering module. So the overall flow is extract audio, transcribe, enhance captions, generate SRT, and finally render video. This modular structure makes our application much easier to understand, maintain, debug, and extend. Now that we have written our pipeline, let's run it and see what happens. So I'm going to run the pipeline directly from the terminal. So Python pipeline.py. As you can see, the pipeline starts executing, but we get an error. Okay, this is actually useful because the error message tells us exactly where Python stopped. The first error points us to our srt.py file. Okay, here. Okay. So SRT here, SRT, let's see. Okay, maybe there is a typo here. Okay, let's see. So SRT. Oh, it says that our caption object doesn't have an attribute called strat. Okay, this is actually a typo, so it should be start. All right. Now let's run the pipeline again. Okay, so here we got our output. So let's check and see if the video is intact. Okay, we have passed the first error, but now we get another problem. This time the problem comes from our captioner.py file. When we look at the results, we notice that only the first caption is being returned. Let's see our SRT file. As you can see here, only the first caption is returned. Let's look at the loop first. Okay, captioner. So inside this loop we process each transcription segment. Okay, then we create a caption object and add it to our list. All right. Oops. The problem is that our return statement is indented inside the loop. If we return from inside the loop, Python immediately leaves the function after processing the first segment. So we only get the first caption. We need to move the return statement outside the loop. Alright, at the same indentation level as the for statement. Now the loop can process every segment before returning the complete list. Okay, let's run the pipeline again. This video, audio, and SRT file are actually replaced by the new output. So let's take a look now at the SRT. Okay, now we got two captions here, as you can see. And now let's look at the video again. Oops, we still have the same problem. Let's check further and see what the cause of the problem is. The pipeline gets further, but we encounter another issue when generating the SRT timestamps. Okay, so there must be a problem with SRT file. Okay, let's check this function, format time, hour, minute, second. Oops. At first glance, this might look correct, but there's a problem with the order of operations here. As you can see, Python evaluates the multiplication before the subtraction. So this expression is interpreted as t minus, and then between brackets integer t times 1000. But that's not what we want. We want to first remove the whole seconds from the timestamp. So we need t minus integer t. This gives us only the fractional part of the time. Then we multiply that fractional part by 1000 to convert it into milliseconds. So the corrected line is this should be here. Alright, now our timestamp calculation is correct. We can run the pipeline one more time. Okay, let's save and run the pipeline one more time. Okay, so these outputs are gonna be replaced again. Okay, now let's see. Alright, we managed to solve that problem. We don't have that problem anymore. This time the pipeline completes all of its stages. First, the audio is extracted, then Whisper transcribes the audio, next Gemma improves the captions, then we generate the SRT file, and finally FFmpeg renders the subtitles onto the video. At the end we should see three outputs: the audio, the SRT file, and the rendered video. So we have just gone through an important part of real-world programming, which is debugging. Notice that we did not randomly change the code. For each error, we looked at the traceback, identified the file and line where the problem occurred, understood why the code was failing, and then made the smallest correction necessary. The three problems were very different. The first was a simple attribute typo, so strat instead of start. The second was an indentation problem that caused the function to return after only one iteration. And the third was an operator precedence problem in our timestamp calculation. This is exactly how you should approach debugging Python programs. Read the traceback, locate the problem, understand the cause, make a targeted fix, and run the program again. So far, we have our video subtitle pipeline working from the terminal. We can give it a video, Whisper transcribes it, Gemma improves the captions, we generate an SRT file, and FFmpeg burns the subtitles into the video. But currently, the user has to run Python code from the terminal. So now we are going to turn that pipeline into a simple web application. The final application will allow the user to open a web page, select or drag a video, click a button, wait while our Python pipeline processes the video, and finally download the subtitled video. We are going to build this progressively using three files: main.py for the FastAPI backend, index.html for the web page structure and JavaScript, and style.css for the appearance. Let's start with the backend. So we create a file called main.py. First, we need to import OS. We are going to use OS for working with directories and file paths. Next, we need Subtitle. Import Subtitle. Subtitle gives us convenient functions for copying and moving files. We will use it when the uploaded video arrives and when we move the final generated video into our output folder. Now let's import the FastAPI component we need. So from FastAPI create our web application, and upload file represents a file uploaded by the user, and request represents the HTTP request coming from the browser. Next, we need two response types. Okay, from HTML response will be used when we return our web page. File response will be used later when the user wants to download the generated video. Now we need the tools for serving our front end. Okay, from Static files allows FastAPI to serve files such as CSS, and Jinja to template allows FastAPI to load our HTML template. Finally, we need to import our existing video processing pipeline from. This is important. We are not rewriting our subtitle generation system. We are simply connecting our existing run pipeline function to a web interface. Now let's create the FastAPI application. So app equals FastAPI. App is now our FastAPI application. The title is simply the name we give to the application. Our application needs somewhere to store uploaded videos and generated videos. So let's define two folders: upload, output. Upload underscore dir is where the original uploaded videos will go, and output dir is where the final subtitled videos will go. We also need folders for our front-end files. os.make dirs create a directory. Exist underscore OK set to true means if the directory already exists, don't produce an error. So when we start our application, these folders will automatically be created if necessary. Now we need to tell FastAPI where our static files are. Okay, app. This line says whenever the browser requests something beginning with /static, FastAPI should look inside our static directory. Our CSS file will be inside this directory. Next, we tell FastAPI where our HTML templates are located. Template. So now FastAPI knows that our HTML files will live inside the templates directory. Now we are ready to create our first web page route. When the user visits / we want to display our index.html. So at app.get. At app.get means we are creating a get endpoint. The / represents the home page, and response underscore class equals HTML response tells FastAPI that this endpoint returns HTML. Now let's define the function. This function receives the browser's request, and now we return our HTML template. We are telling FastAPI to render index.html. We also pass request into the template context. Before we continue with the backend, let's create the front end so we can actually see something. Inside the template directory, create index.html. So index.html. So start with the basic HTML structure. At this point, we have a completely basic web page. Save the file and start FastAPI. So UVcorn, if you don't have it installed, please install it. So pip install UVcorn. Main reload. Now open the application in the browser or on your IDE. You should see essentially a black page because we haven't added anything inside the body yet. Alright, it seems like we forgot to import file. Alright, let's now create the main structure of our application. Inside the body add. We have a main page container. Inside it we have a card. Inside the card we have our header. The header contains our logo, title, and description. Save the file and refresh the browser. We should now see the text and the emoji. It doesn't look very nice yet, but the HTML structure is working. Now we are going to start improving the appearance. Create a static folder and inside it create style.css. Okay, so this is the static folder, and inside it we are gonna create style.css. Alright, then go back to index.html and inside the head add. This tells the browser load the CSS file from the /static path. Now save everything and refresh the browser. Nothing may look dramatically different yet because we haven't written the CSS. Let's start our CSS with a small reset. The asterisk selector targets every element. Box sizing border box makes width and height calculations easier to control, and we remove the browser's default margins and padding. Next, let's define some reusable design values. These are CSS variables. Instead of repeatedly writing the same colors and values throughout our CSS, we give them names. For example, --accent represent our main blue color. Now let's style the body. We make the HTML element take the full height. Now the body. We are giving the page a dark background, setting the font, setting the text color, and adding some subtle gradient. Save the CSS and refresh the browser. Now the background should look much more like a modern application. Next, we will style our page container. 100 VH means the full height of the browser window. Flexbox allows us to center the card both vertically and horizontally. Now style the card. This creates the central panel of our application. We give it a maximum width, background, border, rounded corners, shadow, and some internal spacing. Save and refresh the browser. Now we should have a centered card containing our title. Let's improve the header. This centers the content and create some space underneath it. Now the logo. We are creating a small square around our video emoji. Then let's style the title. And finally, the description. Save the CSS and refresh the browser. Now our header should look like a proper application header. We now have the basic visual structure. Let's add the actual upload area. Go back to index.html. Inside main, after the header, add this code. Now we have a form. Inside it is our upload area, and inside the upload area is an actual file input. Notice that accept equals video / asterisk tells the browser that we are interested in video files. We also have a button. The button starts with disabled because there is no video selected yet. Save and refresh the browser. The uploaded area will appear, but it doesn't look good yet, so let's style it. First, let's make the form a vertical layout. So let's go to CSS file and add some styling code. Now let's style the drop zone. We are turning the upload area into a centered box with a dashed border. Now let's add the hover and drag over appearance. When the user hovers over the area or drags a file over it, the border and background change. Let's also define what happens after a file has been selected. The dashed border becomes solid. Now we need to make the real file input invisible. The input still exists and still works. We are simply making it invisible and placing it over the whole drop zone. So clicking anywhere inside the drop zone opens the file selector. And now let's style the text and the selected file name. The second rule means that if there is no file name, the file name element isn't displayed. So now save the CSS and refresh the browser. Now our upload area should look much more polished. Let's style the Generate Subtitles button. Now let's add the hover effect and the active state. Finally, because the button starts disabled, let's make the state visually clear. Save and refresh the browser. Now we have a proper upload button, although it's currently disabled because we haven't added the JavaScript behavior yet. Now let's go to the HTML file. Under the form in index.html, let's add a place where we can show processing information and the final download button. These elements start empty. Later, JavaScript will dynamically put messages inside it. Now we are ready for JavaScript. JavaScript will control what happens in the browser. First, we get references to the HTML element we need. Each constant now points to one of our HTML elements. This allows JavaScript to interact with those elements. Okay, let's create a function that updates the interface whenever the user selects a file. First, we handle the case where there is no file. We clear the file name, we remove the has-file CSS class, and we disable the button. Now let's handle the case where a file exists. Here we disable the file name, we add the has-file class, which changes the appearance of the drop zone, and finally we enable the button. Now we need to tell JavaScript to call setFile when the user selects a file. The change event happens when the selected file changes. We take the first selected file and pass it to setFile. Save the HTML and refresh the browser. Now click the upload area and select a file. You should see the file name appear and the button become enabled. Notice that we didn't change the HTML manually. JavaScript changed the page dynamically. Now let's support dragging a video onto the drop zone. First, detect when something is dragged over the area. Prevent default is important because it allows us to handle the drop ourselves. We also add the drag over CSS class. Now detect when the file leaves the area. And now handle the actual drop. Again, we prevent the browser's default behavior and remove the visual drag state. Now get the dropped file. Data transfer.files contains the files that were dropped. If a file exists, we put it into our file input. Now the drag and drop interface behaves like normal file selection. At this point, the browser can select a video, but clicking generate subtitles still doesn't send anything to Python. This is where the front end and back end finally communicate. We will listen for the form submission. OnSubmit runs when the user clicks the button. Prevent default prevents the browser from performing its normal form submission. Instead, we will send the request ourselves using JavaScript. So let's get the selected file. If there isn't a file, we simply stop. Now we create a form data object. Form data is designed for sending form fields and files to a server. Now we add our video. Notice that the name is file. This is important because our FastAPI endpoint will also expect a parameter called file. Before sending the request, let's disable the button. And let's show a processing message. Now the user knows that the application is working. We can finally send the video to our backend. Fetch sends an HTTP request. We are sending it to /upload. We are using the post method because we are sending data to the server, and the body contains our form data. Now let's check whether the request succeeded. If the server returns an unsuccessful response, we create an error. Otherwise, we read the JSON response. Our FastAPI backend will eventually return the URL of the generated video. Now we will replace the processing message with a download button. JavaScript takes the URL returned by FastAPI and put it inside the link. If something goes wrong, we want to show a friendly message. Instead of displaying a technical error to the user, we display a simple message. Finally, whether the request succeeds or fails, we re-enable the button. We have created the HTML for our processing message, but we haven't styled it yet. Let's add the CSS. Now the status message. And now the spinner. The important part here is the animation property. We need to define the animation. This tells the browser to rotate the spinner continuously. Now let's save and refresh the browser. The spinner isn't visible yet because JavaScript only created when we submit the form, but the styling is now ready. Now let's style the final download button and the hover effect, and finally our error message. Let's save and refresh the browser. Now our front end has all the visual component it needs. The front end is ready to send a video to upload. Now we need to create that endpoint in main.py. Let's start with app.post upload async. This creates a post endpoint called /upload. Upload file represents the uploaded video, and file tells FastAPI that this parameter must come from an uploaded file. Now we need a path where we will save the uploaded file. Input path os.path.join. We are combining our upload directory with the original file name. Now open that path for binary writing with open input path write binary as buffer. WB means write binary. That's necessary because a video is binary data. Now copy the uploaded file into that location. Shutl.copy file object file.file buffer. So at this point, the browser has sent the video to FastAPI, and FastAPI has saved it inside our uploads folder. Now comes the most important connection. We already have our complete subtitle pipeline. So instead of rewriting any of that logic, we simply call it captions srt path output path run pipeline input path. Our uploaded video becomes the input to run pipeline. The pipeline processes it exactly as before, following the same order: audio extraction, transcription, caption enhancement, SRT generation, and video rendering. And it returns our captions here, SRT path, and final video path. The pipeline creates the final video, but we want our web application to keep generated videos inside output directory. So let's create the final destination. Final output os.path.join os.path.base name output path. os.path.basename extracts just the file name from the output path. Now we move the generated video. Subtitle.move output path final output. Now our final video is inside the output folder. The front end is waiting for a JSON response containing a video URL. So we will return one. Return video URL and then fstring /download curly braces os.path.base name and final output. All right. This creates a JSON object containing the URL of the generated video. The JavaScript receives this response as data. That's why we could previously write data.video URL. The front end and back end are now connected. We have one final back end piece. When the user clicks download button, the browser will request download. So let's create the endpoint at app.getDownload /file name div download underscore video file name stir. All right, file name is a dynamic path of the URL. FastAPI will give us the file name as the file name argument. So now we construct the path equals os.path join output dir file name. Here we are looking inside our output directory. Finally, we return the video. Return file response. We open brackets, we give it path and media type. Okay, media type equals video /mp4 and file name equals file name. File response sends the file back to the browser. Media underscore type video mp4 tells the browser that this is an mp4 video, and file name gives the file its name. We have one final CSS section. We want the application to work well on smaller screens, okay, or what we call responsiveness. So we open CSS file and we add this line of code. This means that the following CSS will only apply when the screen width is 480 pixels or less. Okay, now we adjust the card padding. Then we make the title slightly smaller and we make the upload area slightly shorter. Now save the CSS and refresh the browser. Now let's test the entire system from beginning to end. First, make sure Ollama is running because our pipeline uses Gemma. Then start FastAPI. Okay, UVcorn main app reload. Open the application in the browser. Now let's open it and see. Open the application in the browser and select a video. So this one. Notice that the file name appears. And notice that the generate subtitles button becomes enabled. Now click generate subtitles. As you can see, the browser sends the video to post upload, and FastAPI receives the video and saves it. Then FastAPI calls run underscore pipeline with the input video we have just given it. All right, and our existing Python pipeline processes the video. Okay, when processing finishes, FastAPI moves the generated video into output. Okay, here, as you can see here is our generated video. Then returns the download URL, as you can see here. JavaScript receives that URL and creates the green download button. Finally, when we click that button, the browser requests get/download/filename. FastAPI returns the generated mp4 file. Now let's click on download button and see. As you can see here, we are asked to save the video in the folder we want. So that means the application works perfectly. One more thing we do before we end this video, let's open it in a browser and see if it works as it should. As you can see here, the design looks nice, and then we try to upload a video. Okay, then generate subtitles and wait for the video to be processed. Okay, the video is ready. Let's download it. Okay, and as you can see here is our video. Let's play it. If you've ever wanted to analyze audience reactions, gather feedback, or explore trends hidden inside comment sections, This video will walk you through the entire process step by step. As was expected, the captions were generated correctly and the application works perfectly. And that's it. We started with a simple idea, which is uploading a video and automatically generate subtitles. But along the way, we built an entire application around that idea. We used Whisper to turn speech into timestamped text. We used Gemma to improve the caption while keeping their original meaning. We converted those captions into an SRT subtitle file. We used FFmpeg to burn the subtitles directly into the video. And finally, we connected everything to a FastAPI backend and a browser-based front end, so the whole process can be triggered simply by uploading a video. More importantly, this project demonstrates something that is extremely important when learning software development. Real applications are built by connecting different pieces together. You don't need one giant piece of code that does everything. You build small components, give each component a clear responsibility, and then connect them into a pipeline. In our case, the journey is essential. We started with a video, then audio, transcription, AI enhancement, SRT, rendering, and finally downloading. And that's what makes this project more than just a subtitle generator. In practice, it's a practical example of how AI, back-end development, front-end development, and media processing can come together to create a complete application. If you followed along and wrote the code yourself, you have something much more valuable than a finished project. You have a better understanding of how real-world applications are actually put together. Thanks for watching, and I will see you in the next project.